Hello everyone, what's up? Welcome you all to this channel. My name is Shiraz Ahmed. Here is a brief profile about me. So today my friends will start chapter number 2 on pressure and pressure measurement. As we all know that pressure is a very important property of a fluid as it will help us to understand the behavior of the fluid and to predict the behavior of the fluid. Apart from this, it will help us to understand various physical phenomena, for example, cavitation that occurs in case of turbine and pump. So my friends, at the end of this chapter, you will be able to understand what is pressure, various pressure measurement devices, for example, piezometer, manometer, etc., vapor pressure, and also you will be able to understand phenomenon called cavitation. So let us start our first topic, that is pressure. So what is pressure? Let us try to understand what is pressure. So pressure is nothing but a normal force exerted per unit area. Okay my friends. So I have considered an example here. So in this case I am trying to hammer a bowling pin on the wall. Okay, what happens? It will be very difficult to penetrate a bowling pin, right? You'll feel that it is taking a lot of effort to penetrate the bowling pin. Okay, but if I have given you a nail and you try to apply the same force, as in this case, you try to apply the same force, what happens? The nail would be more likely to penetrate inside the wall. Why this is happening? Let us try to understand. Bowling pin is not able to penetrate, but the nail is able to penetrate, is more likely to penetrate inside the wall with the same amount of force. So why it is happening? It is because of the pressure. So in case of nail, the surface area of the nail is very small surface area. So due to small surface areas compared to bowling pin, the same force, when the area is smaller, the same force will have a larger amount of pressure. So when you apply a same force in case of a nail, due to its smaller normal area, the pressure generated in case of nail is higher as compared to bowling pin. So nail is able to penetrate, and while the bowling pin will be difficult to penetrate inside the wall. Okay, from this example we also say that pressure is compressive in nature, because when you try to apply a force on this bowling pin or nail, what you are exactly trying to do? You are trying to do you are trying to compress the nail or the bowling pin. So what is pressure? Pressure is compressive in nature. Okay my friends, it's clear? Till now everything is clear to you all. So let us move to our next slide. So this was all about pressure in case of solid. But let us try to understand how we will define a pressure in case of fluid, because it is unimaginable to hammer a pin inside a fluid, right? So let us try to understand pressure in case of fluid. So the first thing comes in our mind is, that is our home application, if we'll our daily life situations, that when a bucket is full of water, right? This is the bucket and it is full of water. Okay my friends, so at the bottom of this bucket, this fluid will apply some pressure, right? You'll feel when a submerged object is there, like let's suppose if you are swimming and you are inside the water, you'll feel certain amount of force that is applied by the fluid on you. Similarly, when the water is filled, the bucket will feel some amount of force at the bottom. What is this force? So this force is applied due to the weight of the fluid. So in first example we can say that fluid due to its weight, okay, applies a force, and when that force we divide by the area, we'll get the pressure. So this is the first thing. Okay, so how the pressure in case of fluid, due to its weight, the fluid will have some pressure. So if I consider a column here, let's suppose if I consider a column here, okay, the acceleration due to gravity is down, so weight will be downwards, right? So in this case, if I consider this column here, it will be the atmospheric pressure, right? Because it is in atmosphere, it is a free surface. So when I go down, the more I go down, the more weight of the fluid will be on the top of it, right? So the more the weight of the fluid, the more the pressure will be. So as we go down, the pressure will increase. Okay. So now let us understand another concept of pressure inside a fluid. So the second thing is enclosed. When a fluid is enclosed, so one is due to its weight, but when fluid is enclosed and we have applied external, this, let's suppose this surface is movable and I have applied a force from outside. So this will create additional pressure apart from weight. Okay, so in case of enclosed fluid, there is another pressure that is created, which will be created due to external force applied. So the various example for this case is flow through pipes, right? So if I apply a force or pressure from external devices like pump or compressor, the fluid will have some additional pressure apart from its weight. Okay, so that is the second scenario. So now we understand what is pressure in case of fluid. So let us try, pressure is a property. So let us try to understand whether the pressure is a scalar or vector. Because if it is a property, then it should be either vector or scalar. So as we studied in our lecture number 1, as per Pascal's law, that when the fluid is at rest, okay, the fluid has no direction, that is it have infinite direction. So Pascal's law what says that in case of fluid, if I consider a point here, the pressure will be in all direction. So there will be no finite direction where we can say that pressure is applied in this direction. So when there is no finite direction, then it is a scalar quantity. So what is pressure? Pressure is a scalar quantity. Now we are able to understand. So this thing we have learned in the lecture number 1, that Pascal's law states that at a point inside a fluid, the pressure is applied in various direction, equal amount. It is distributed in various direction in equal amount. Okay. So now we understand that what is pressure? Pressure is force per unit area. In case of fluid, the pressure is generated due to two reasons. One is due to its weight, the other is enclosed container, and the next thing we learn that pressure is a scalar quantity. Okay, my friends. So let us try to understand another thing for pressure. So I have considered a fluid inside a container. Okay. So what we have learned just now, that pressure is in case of fluid when it is at rest due to its weight. So weight, the acceleration due to gravity is downward, so the pressure will increase in downward direction. Why? Because I have considered a column here, okay, and if I move down, if I am here, let's suppose, and I move down till here, so now in this case I have more weight of fluid above me as compared to this case. So when there is more weight, then there will be more pressure at this point, right? Let's suppose here the pressure is P plus delta P, here the pressure is P, and I have moved by a distance delta H, right? So what I can say, P, and the area of this column is A, let's suppose, okay. So P is some amount, okay. So now what is P plus delta P? P plus delta P minus P. What is this quantity? Let us try to understand. P plus delta P minus P means difference between these two pressure. What it will be? It will be the weight between these fluids, right? Between these 2 points. So whatever the fluid is there, that extra pressure will be added to this P and will get P plus delta P, right? So delta P is nothing but the additional weight between two points, that is point number 1 here and point number 2 here, or I can say in between delta H height, okay. So what is the weight between these 2 points, or I can say if I'll try to balance the force, right? So P plus delta P, right, that is in upward direction, minus P, that is in downward direction. So net it is up, force is in upward direction. If I multiply it by, this is the force due to pressure and the direction will be upward, okay. And if I try to calculate the weight of the fluid between these 2 points for delta H, that is density into volume into G. So density is rho. Let's suppose consider the density of this fluid is rho. So density into volume. What is the volume of that fluid in that column is A into delta H into G. This is the weight, right? It will be downward. So if I balance the pressure, because the fluid is in static condition, it means that fluid is not moving. So Fp will be equivalent to its weight. And what is Fp? P plus delta P minus P into A rho A delta H into G, okay. A will get cancelled, P will get cancelled with P. So what is delta P? That is differential pressure, is nothing but rho G into delta H, right? In previous lecture we have learned what is rho G. It is specific weight, right? Omega into delta H, okay. So this we have learned differential pressure across column. What we have learned? Differential pressure of fluid due to its weight, right? So now if I'll say I will say that I have given a pressure here as a P1. Okay, the density of the fluid is rho and the acceleration due to gravity is g, and I want to find vertically downward point. Let's suppose here I want to find the pressure P2 here at a height h from here. Okay, this is a problem statement. You can stop the video for a moment and try to solve it by yourself. Okay, now let us try to solve this question, that what is the pressure at this point, that is P2. So as it was explained in the earlier session, that delta P, that is differential pressure due to weights between 2 points, is rho g delta h, where rho is the density of the fluid and g is the acceleration due to gravity. So in that problem, this is the fluid, okay, and I know the pressure here, that is P1. I want to find the pressure here, that is P2. Okay, so what is delta P? Delta P is nothing but P2 minus P1, which is rho g. What is the difference between these two heights that was given in the question? It is h. So delta h is nothing but h. So what is the pressure P2? P2 is nothing but P1 plus rho g h. Okay, my friends. So now this is how we can solve the problems in columns. Okay, we can solve the problems for pressure in columns. So let us try to develop one generic concept. Okay, so let us consider this is any point, that is P, where the pressure is P in the fluid. Any fluid, any column, anything, anywhere it is, somewhere, and the acceleration due to gravity is downward, that is g. So if I try to find pressure either above or this point or below this point, then what should be the logic? So the pressure above or below, let's suppose it is P dash, I have defined. Okay, so it should be in terms of P, either P plus rho gh or P minus rho gh. So it can be either plus or minus, right, this P dash pressure. So if we are going downward from that point, okay, then as we can see, the acceleration due to gravity is downward, and when we move downward, additional weight of the fluid will come in between. So indirectly we can say it should be P plus rho g. We don't have to remember this formula at all. Okay, what, at any point if pressure is given and I am moving downward, it means some additional weight of the fluid is coming between, so plus. And if I move up, then this much of the fluid weight should be subtracted, so it will be P minus rho gh. So in any column, whether it is pipe or bucket or anywhere, okay, let's suppose consider this, these are the two columns, okay, U-tube column, and I have a pressure P here. I want to find out pressure here. So what it is I'm moving downward, so it should be plus P plus whatever this height is, 20 centimeter or whatever. I will add that multiplied by density and acceleration due to gravity. Clear? So now this is about the column, and this particular concept will be used very frequently in manometer, in U-tube manometer, in solving various problems related to this. Okay, so try to memorize this logic, when it is plus, when it is minus. Okay, so I hope it is clear to you all. So now we can move to our next concept, that is inclined pipe. So till now what we have seen, it is straight pipe, right? So if it is straight pipe, if I am moving downward, then P plus rho g h, the P dash. But if what happens if it is inclined pipe and I am moving in inclined pipe, okay, so let us consider an inclined pipe. Okay, so this is 1, 2, and now I am having inclined pipe, right? This pipe is making an angle theta with horizontal. Okay, so now I have a fluid here. Okay, and if I move by distance L inside this pipe, and here the pressure is P, what will be the pressure at this point, P dash? Okay, it's simple. Question is clear to you all. So it is very simple concept. Okay, whatever I have explained in previous case is valid in this case also. So here also the acceleration due to gravity is vertical. Okay, so this weight of the fluid will not apply in this direction, it will apply on this direction only. Okay, so what will be the actual height or actual height that is contributed to the weight between these 2 points is this height. Okay, so this is the actual height that will contribute to the weight of the fluid. Why? Because acceleration due to gravity is vertical. If it would have been at an angle theta, let's suppose this is g dash, so let us consider an imaginary case where the acceleration due to gravity is inclined. Somehow I have made it inclined, okay, in this inline direction. Then what will be the weight of the fluid that is trapped between these 2 points? Which is the height that is contributing in this case? It will be L. But now for this case, this is not the acceleration due to gravity. Acceleration due to gravity is this one, that is vertical. So effective height that will contribute to the weight of the fluid will be this. So what is this H? H is nothing but L sine theta. Okay, and I'll say effectively I'm moving downward, right? I'm moving where? Downward. So what will be the P dash? P dash equals to P plus or minus. I am moving downward, so weight will be add on. So plus density G into height, effective height, that is H, nothing but L sine theta. So let us solve a problem on inclined pipe. So the problem says there is inclined pipe which is making an angle theta here. Okay, and it is filled with a fluid. And this pipe is connected to a pressure line where the pressure is maintained as P, okay, which is greater than atmospheric pressure. Okay, so the question says, let's suppose I draw a horizontal line here. Okay, so what is the rise in the fluid in this column, that is L? What is the value of L if the atmospheric pressure is P atm and the diameter of the pipe is constant throughout? Okay, my friends, density of the fluid is rho, diameter of the pipe is d throughout. Okay, so what is this length L? Let us try to solve this problem. So I have given a pressure P here, and as per the Pascal's law that we have discussed in lecture number 1, that in a fluid in horizontal direction, if the acceleration due to gravity is vertical, so the constant pressure line will be perpendicular to G, that is horizontal direction. We will study this constant pressure line in next topic. What is the constant pressure line? Okay, so it is nothing but where the pressure remains constant. So when the acceleration due to gravity is vertical, okay, the constant pressure line is the perpendicular to G, that is horizontal. So here the pressure is P, so here the pressure will be P, right? And because this is a free surface, so here the pressure will be P atmospheric. Okay, So now, as per the column law that we have discussed earlier, as per the column rule that we have discussed earlier, the relation between PATM and P. So let's suppose I am here, I want to move upward. So what is the effective height that is contributing to the weight of the fluid is L sine theta. That is the height that is contributing to the weight of the fluid. And if I am here at this point, so this point the pressure is given and I am moving upward, so it will be the minus, and minus of what? Minus means weight of the, that is rho g into effective height, that is L sine theta. So I have moved this height, right? So this will be the pressure at which point? This point, right? So what is the pressure at this point? Is nothing but PATM. So if I take this this term on left side, then it will be rho g L sine theta equals to P minus P ATM. Then the rise in the fluid column is L, which is given by P minus P ATM upon rho g sine theta. Okay, my friend. So this is the answer. Now let us move to our next topic, that is constant pressure line. What is constant pressure line? So it is nothing but a line or a point, set of points where the pressure remains constant throughout. Okay, so it is the locus of constant pressure. So we consider case number 1 where the acceleration due to gravity is vertical. So in this case, if I consider a fluid in a container, so the pressure will change only in the vertical direction because of the weight of the fluid, and horizontal line that is perpendicular to the G, on that the pressure will remain constant and it will be the constant pressure line. Horizontal line will be the constant pressure line. So that is why if you jump from one column to another column in the same horizontal direction, the pressure will remain same. And this concept will be highly used in the manometer concept. Okay. So if this is the same fluid, remember this point also, this should be same fluid. As I say, in horizontal direction, the pressure remain constant, that is constant pressure line is the horizontal line. So if pressure here it is P, so if I draw a horizontal line and it is the same fluid, then here what will be the pressure? It is P, right? And if I move up by distance h, then what will the pressure here? It will be P minus, because I am moving up, so minus term rho g into h, where rho is the density of this fluid, or height, h is the height by which we have moved. So this is the first case. Okay, now we have a second case where what I have done, in this case also I have made a bucket full of fluid, and now what I did, I start rotating this bucket by speed omega. So in this case, the top surface of the fluid will become like this. Okay, so and this is the free surface, right? So free surface means here the pressure will be constant. So this is the constant pressure line, and if I draw the lines parallel to this, then all will be the constant pressure line. Okay. So now let us try to understand what could be the reason behind this. Before trying to understand the reason behind this, let us consider another example. Okay, in that case, what I did, I placed the bucket of water on a cart which is moving with acceleration a. Okay, my friends. So here the acceleration due to gravity is g, right? Okay, and now if I make this cart at rest, so I will apply opposite direction acceleration. So this fluid will have acceleration in this direction, pseudo acceleration. So to make this thing at rest, what I did, I have applied another pseudo acceleration in opposite direction of same amount, right? So now this is considered as a net rest condition. Okay, so if I'll combine A and G, there will be a net acceleration in this direction. Okay, my friends, so this is A net. So what happened in this case? Now weight of the fluid will be in this direction only, right? Weight of the fluid will be in this direction, that is A net, perpendicular to this. So if I draw a line perpendicular to this line, that will be the constant pressure line. So these lines are the constant pressure line. Okay, my friends, these lines perpendicular to that will be constant pressure line, and this will become the free surface, after which there will be no fluid, right? Why this is now free constant pressure line? Because it is perpendicular to the net acceleration. Here also, in this case also, what is the constant pressure line? Perpendicular to the G, that is net acceleration. But we have one more acceleration, A, in this case. So because of that, there will be additional acceleration and will cause a net acceleration, that is in this direction, and perpendicular to this will be constant pressure line. Okay, my friends. Similarly here, if we'll see, okay, let's suppose I have drawn a horizontal line. Okay, so this point will experience acceleration here downwards, and as this was a pseudo acceleration, right? Similarly here a pseudo acceleration will appear, that is centrifugal acceleration, that is omega square into r, where r is the distance from this point. Okay, because of this there will be a net acceleration here, and the constant pressure line will become net acceleration in this direction. The constant pressure line will become perpendicular to this, that is this line, right? It will be like this. So this will be the constant pressure line in this case. Okay, clear? I hope now this concepts of constant pressure line is clear to you all. So let us move to our next topic, that is unit of pressure. So how we have defined the pressure? Pressure is nothing but the force per unit area. What is the unit of force? Is Newton. What is unit of area? Is meter square. Okay, so this is in SI unit. We call it as a Pascal. Okay, another unit is bar, and the relation between bar and Pascal is 1 bar equals to 10 to the power 5 Pascal. Okay, another unit is ATM, that is atmospheric pressure. What is the value? 1 ATM equals to 101.325 kilo Pascal. So these are the few units of the pressure. Okay, my friends. So now let us try to understand what is atmospheric pressure. In layman term, we can say, let's suppose I have drawn earth here. So what is above the earth? What do we have above the earth? Is air, right? What is the composition of air? It is 92%, nitrogen 79% approximately, oxygen approximately 21%. Okay, my friends. So this air exerts pressure on earth. Okay, and this pressure is called as a atmospheric pressure. Unit we have already seen, that is atmospheric pressure is nothing but 1 atm and its value is 101.325 kilopascal. Okay, so my dear friends, this is all from our this lecture. The remaining topic related to the pressure measurement will be covered in subsequent lectures. For more videos and regular update, subscribe to this channel. Thank you all for watching this video.